Why we are going for the testing of transformer? So in order to find out the losses, you can go for the testing as well as the efficiency of a single phase transformer. By conducting open circuit test and short circuit test, SC test, we can determine the efficiency. By knowing the losses, we can determine the efficiency. That is called the predetermination of efficiency. Without conducting or without applying an external load, if we conduct these two testers, we can calculate the efficiency as well as the voltage regulation. And there are three types of tests. One is open circuit test, short circuit test, and another one is Ammeter test. Coming to the first one, open circuit test of single phase transformer. Open circuit means we are giving the supply to one winding and another winding should be open circuited. If you observe here, so this is the transformer. So this one is transformer primary and this is a transformer secondary. We are applying the voltage to one winding and another winding is open circuited. So what is the EMF equation of a single phase transformer? 4.44 into B max into AN into F into N. So if B max is directly proportional to E divided by F, the remaining all are constants once design is over, and it is directly proportional to V divided by F. What are the main objectives of this test are to find out the iron losses. Wi means to find out the iron loss in transformer core, and to find out shunt branch parameters of an equivalent circuit. Shunt branch parameters of an equivalent circuit. So these are called the two objectives to find out the open circuit test. And one more object is also there, to separate the core losses into hysteresis losses and eddy current losses. So here we are applying a variable AC voltage with the help of a single phase variac. Single phase variac means variable AC supply. And we can call it as a auto transformer. Single phase auto transformer, and we can call this also called dimmer stat. So from the supply we are getting phase and neutral, and that is given to auto transformer through DPST switch. By closing the DPST switch, here the phase will be available and neutral is available here, and this point is now output of the auto transformer phase and neutral. By varying the auto transformer, we can apply the variable voltage and the frequency is constant. By applying rated voltage at rated frequency, the Bmax in the transformer core is also rated. By keeping one of the terminals, output terminals, one of the terminals means either input terminals or output terminals, but by keeping output terminals as open circuit condition, then this test is called the open circuit test. So this test is conducted at the low voltage side. Why? Because at the low voltage side, the no load current value is more. At LV side, I0 is more. That's why that is easily indicated by the ammeter. So that's why this test is conducted at low voltage side rather than high voltage side. And this voltmeter reading is V and the ammeter reading is I0. So V and the ammeter reading is I0, and from this wattmeter we are getting iron losses, a small amount of copper losses. W is equal to V into I naught cos phi naught minus I naught square into R1. The I naught value, we can know that I naught value is very small, that is 5 to 8% of full load current. The I naught value is 5 to 8% of full load current. It's very small. The no load copper losses will be negligible. So that's why whatever the wattmeter reading indicates the iron losses in a transformer core, the first main objective is over, and the second main objective is to find out the shunt branch parameters. So from these core losses, V1 I naught cos phi naught, and the V1 is low voltage rated voltage, as a cos phi naught is equal to WOC by V naught I naught. So here V1 is equal to V naught is the rated voltage, so V rated, all are same here. And from the no load phasor diagram, if you observe that the practical transformer is operating under no load condition, so one magnetizing component of current is required to produce the flux, and wattful component of current is required to meet the core losses. By adding these two, then I am getting the resultant current, that is I naught. The angle between supply voltage and the no load current is phi naught, where phi naught is called the no load power factor angle. Phi naught is called the no load power factor angle. And the cos phi naught is approximately equal to 0.2 lagging. Why? Because of inductive nature of the winding. The angle between V1 and IM is exactly 90 degrees, and it consists of some resistance is also there to meet the core losses. It will shift upwards. Phi naught is in the range of 75 to 80 degrees. So IW, from this triangle we are getting the equations. IW is equal to I naught cos phi naught, and IM or IMU is equal to I naught sin phi naught. And so we can calculate the shunt branch parameters of an equivalent circuit. What are the shunt branch parameters of an equivalent circuit? So this is R naught, the core loss component is represented with R naught, and magnetizing component is represented with X naught. The current drawn from this is no load current is I naught, and the current which is flowing R naught is IW, and the current flows through X naught is I mu. I naught bar is equal to I mu bar plus IW bar. So here we are applying supply voltage. So as we already discussed in the practical transformer is operating under no load condition, the R naught formula is V divided by IW, that is V1 divided by IW. So V1 is indicated by the voltmeter, and IW is calculated. Shall I calculate R naught? R naught, yes, R naught is calculated. This R naught is the equivalent circuit of the shunt branch parameters, and X naught similarly V1 divided by I mu, where I mu is equal to I naught sin phi naught. If you want to find out the conductance, so V naught square divided by R, 1 by R is equal to G naught. Exciting conductance G naught is equal to WOC divided by V square, and this is a susceptance I mu divided by V naught. So by conducting this open circuit test, you can find the losses. That loss is called the iron losses. And by conducting open circuit test, we can only find iron losses, not copper losses. And one more thing is also there, that is we can find out, or we can separate the hysteresis losses and eddy current losses from iron loss. And this test is conducted at the variable voltage. This test is conducted at variable voltage, so we vary, and variable frequency is also varied. By maintaining Bmax is constant. Note down the voltmeter reading, ammeter reading, and Gera, and Bmax is constant means hysteresis loss is directly proportional to F, and eddy current loss is directly proportional to F square. And if you draw the curve between iron losses versus frequency by frequency versus frequency, here I am getting the A value, and slope is theta. This length should be equal to B. So iron losses by F is equal to A plus BF. So from this you can calculate the, or you can separate the hysteresis losses and eddy current losses from iron losses.